Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the basic considerations for thermodynamic cycles. Two important areas of application for thermodynamics are power generation and refrigeration. Both are usually accomplished by systems that operate on a thermodynamic cycle. Thermodynamic cycles can be divided into two general categories: power cycles and refrigeration cycles. Thermodynamic cycles can also be categorized as gas cycles and vapor cycles, depending on the phase of the working fluid. In gas cycles, the working fluid remains in the gaseous phase throughout the entire cycle, whereas in vapor cycles, the working fluid exists in the vapor phase during one part of the cycle and in the liquid phase during another part. Thermodynamic cycles can be closed and open cycles. In closed cycles, the working fluid is returned to the initial state at the end of cycle and is recirculated. In open cycles, the working fluid is renewed at the end of each cycle instead of being recirculated. In automobile engines, the combustion gases are exhausted and replaced by fresh air fuel mixture at the end of each cycle. The engine operates on a mechanical cycle, but the working fluid does not go through a complete cycle. Heat engines are categorized as internal combustion and external combustion engines, depending on how the heat is supplied to the working fluid. In external combustion engines, heat is supplied to the working fluid from an external source such as a furnace, a geothermal well, a nuclear reactor, or even the sun. In internal combustion engines, this is done by burning the fuel within the system boundaries. In this project, various gas power cycles are analyzed under some simplifying assumptions. Most power-producing devices operate on cycles. A cycle that resembles the actual cycle closely but is made up totally of internally reversible process is called an ideal cycle. Reversible cycles such as Carnot cycle have the highest thermal efficiency of all heat engines operating between the same temperature levels. Unlike ideal cycles, they are totally reversible and unsuitable as a realistic model. Modeling is a powerful engineering tool that provides great insight and simplicity at the expense of some loss in accuracy. We have to keep the complexity at a manageable level and utilize some idealizations. Most power-producing devices operate on cycles, and the study of power cycles is an exciting and important part of thermodynamics. The cycles encountered in actual devices are difficult to analyze because of the presence of complicating effects such as friction and the absence of sufficient time for establishment of the equilibrium conditions during the cycle. When the actual cycle is stripped of all the internal irreversibilities and complexities, we end up with a cycle that resembles the actual cycle closely, but is made up totally of internally reversible processes. Such a cycle is called an ideal cycle, as shown in figures 10.1 and 10.2. Heat engines are designed for the purpose of converting thermal energy to work, and their performance is expressed in terms of the thermal efficiency, eta Th, which is the ratio of the net work produced by the engine to the total heat input. The Carnot principles shown nobody can develop a cycle more efficient than the Carnot cycle. Then the following questions arises naturally. If the Carnot cycle is the best possible cycle, why do we not use it as the model cycle for all the heat engines instead of bothering with several so-called ideal cycles? The answer to this question is hardware related. Most cycles encountered in practice differ significantly from the Carnot cycle, which makes it unsuitable as a realistic model. Each ideal cycle discussed in this project is related to a specific work-producing device and is an idealized version of that actual cycle. The idealizations and simplifications commonly employed in the analysis of power cycles include: Assumption 1. The cycle does not involve any friction. Therefore, the working fluid does not experience any pressure drop as it flows in pipes or devices such as heat exchangers. Assumption 2. All expansion and compression processes take place in a quasi-equilibrium manner. Assumption 3. The pipes connecting the various components of a system are well insulated, and heat transfer through them is negligible. In gas power cycles, the working fluid remains a gas throughout the entire cycle. Sparking ignition engines, diesel engines, and conventional gas turbines are familiar examples of devices that operate on gas cycles. In all these engines, energy is provided by burning a fuel within the system boundaries. That is, they are internal combustion engines. The actual gas power cycles are rather complex. To reduce the analysis to a manageable level, we utilize the following approximations, commonly known as the air standard assumptions. Let's talk about the air standard assumptions for power cycles. Assumption 1. The working fluid is air, which continuously circulates in a closed loop and always behaves as an ideal gas. Assumption 2. All the processes that make up the cycle are internally reversible. Assumption 3. The combustion process is replaced by a heat addition process from an external source. Assumption 4. The exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. Another assumption that is often used to simplify the analysis even more is that air has constant specific heats whose values are determined at room temperature. When this assumption is used, the air standard assumptions are called the cold air standard assumptions. A cycle for which the air standard assumptions are applicable is frequently referred to as an air standard cycle. Okay, that's all for this task. Thank you very much and see you next time.